In the last two lectures, we spent quite a lot of time with Lagrangian mechanics, and now we've gained a lot of familiarity with some of the machinery that we have available to us when we start with a Lagrangian. We're ready to apply it to a very classic example, to orbital mechanics. Now, of course, orbital mechanics was one of the first topics of interest for 17th century physicists, and this continued into the 18th century when Euler and Lagrange developed their formalism. The reason there is that even though classical mechanics appears, all over our daily lives, the motion of heavenly bodies is pretty inexplicable unless you have some greater formal system, and those bodies aren't impeded by anything else. They aren't competing in some sense with all kinds of other things that are not easily described by classical mechanics. And so we find that orbital mechanics is one of the first things that we always encounter when people start talking about either the Newtonian formulation or the Lagrangian formulation. And of course, we could treat this using both. But in order to practice the machinery that we've been learning, let's do it all with Lagrangians. Now, I'll start out this discussion assuming only one thing, that we're in 3D and that we have a central conservative potential. All right, so let's go ahead and, with that in mind, start out writing our potential. I'm going to assume that we have two bodies. So, okay. With a central force between them. We've talked both about a sort of central force between two objects as being a force that is parallel to the line between the objects. And we've talked about a central force on a single object in a given coordinate system as being one that points toward or away from the origin. In this case, I mean the former of those two. Okay, so let's draw a little picture. Here's M1, here's M2, and here's the line between them. So what we have is that F of 2 on 1, which I've denoted F12, is on that line, as is F of 1 on 2, which I'll denote F21. All right, now we're ready to start writing down the Lagrangian. The Lagrangian is 1/2 M1 times the R1 dot vector squared. I should say it's norm squared, plus 1/2 M2 times the R2 dot vector squared minus U of R1 and R2, whatever that may be. Now we're going to start hitting this Lagrangian with assumptions to try to get it into something that we can work on much more easily. The first assumption, so let me write this out, assumption 1, is that the system is translationally invariant. Okay, what do I mean by that? Well, if I take this entire system and translate it all over here, then I should find the same dynamics playing out over here as did over there. That means that this U should not depend on R1 and R2 independently, because again, if I shift these both by the same constant vector, I should find that I have the same potential energy. So what I should instead have is that U depends on the difference between these two vectors. Okay, so let's point that out from assumption 1. This is going to become U of, actually let me say this entire term will become U of R1 minus R2. All right, next, because we have R1 and R2 appearing in this combination here, it seems like we want to change generalized coordinates. So we have here 6 generalized coordinates, assuming that we're working in 3D. We have 3 associated with R1 and 3 associated with R2. So what we'd like to do is get 6 different generalized coordinates. We know that's the number that we'll need, but we would like to include R1 minus R2 as one of those. So let's give that a name. Okay, so next we will say R, by definition, is R1 minus R2. All right, that's 3 generalized coordinates, so we need 3 more. And there are a number of different choices that we could make. For instance, we could choose either R1 or R2. But somehow that doesn't have the nice symmetry that we kind of see in this problem, where M1 and M2 are still being treated in the same way. An object that we could pick that does preserve that nice symmetry in a certain way is the center of mass. So let's use that to be our other 3 generalized coordinates. Remember that the center of mass is defined to be M1R1 plus M2R2 over capital M, where capital M is the sum of the 2 masses. All right, now that we have our chosen generalized coordinates, we're going to need to substitute them into the Lagrangian. Remember, that's what we do when we choose a new set of generalized coordinates. So we'll need to first figure out what R1 and R2 are in terms of these 2 new variables. Then we'll need to figure out what R1 dot and R2 dot are. Okay, to do that, first, let's take this equation, this first equation, and multiply it by M2. So I'll say M2R is equal to M2R1 minus M2R2. Now I'm going to take the second equation and multiply it by capital M. So I'll get M times R is equal to M1R1 plus M2R2. And notice that now if I sum these 2 equations together, I'll get the following. M2R plus capital M, capital R, is equal to, well, M1 plus M2 times R1, but that's capital M. So capital M, R1 plus 0. So this allows me to solve for R1. R1 is equal to capital R plus M2 over capital M times little r. Now let's do the same thing again, but in this case, we'll multiply by not M2, but minus M1. Okay, so minus M1 times R is equal to minus M1 R1 plus M1 R2. And then we'll take the same equation for our second equation. So capital M R is equal to M1 R1 plus M2 R2. Okay, once again, we'll sum these together. Actually, let me, just to be super clear about what equations I actually want, let me box this one. Okay, and then let's get another one. So in this case, we have capital M, capital R minus M1 times little r is equal to 0 plus M1 plus M2 times R2, but that's capital M, R2. And that implies that R2 is equal to capital R minus M1 over capital M times little r. Okay, so that's our second boxed equation. Now, really quickly, let me notice that it's really easy to write the time derivatives of R1 and R2, since these are just linear equations in the new generalized coordinates. All right, so we have R1 dot is equal to capital R dot plus M2 over M times little r dot. And down here we have R2 dot is equal to capital R dot minus M1 over capital M little r dot. Great. Now let's substitute those back into this Lagrangian. I'll actually use the space down here to do that. So we'll have that L is equal to 1/2 of M1 times, okay, well, for R1 dot squared, I need to take this equation and notice that I can expand it out. What I'll get is this first vector squared plus 2 times the cross term, which will involve the dot product, plus this second term squared. Okay, so I'll have R dot squared plus 2 m2 over capital M, capital R dot, little r dot, plus m2 squared over capital M squared, little r dot squared. All right, now for my second term, I'll have 1 half m2 capital R dot squared. Then here I have a minus sign, so I have minus 2m1 over capital M, r dot, little r dot, plus m1 squared over capital M squared, r dot squared. Then finally I have minus u of r. That's the whole reason that we've made this substitution in the first place. All right, now if we look carefully, we see a really nice cancellation happens. Here, this term is plus 2 times m1. Actually, the 2 cancels with this half. So this term, if I multiplied everything out, would be m1 times m2 over big M times r dot, capital R dot, little r dot. This term down here would be minus m1 times m2 over M, capital R dot, little r dot. So they are equal and opposite, and they cancel. Meanwhile, these first two terms can be combined because they both have a factor of 1/2 and then a factor of r dot squared. And if I combine them, I'm going to get m1 plus m2, which gives me a capital M. That's quite nice. Lastly, I'll have a term over here that doesn't nicely combine, but where I can do one step. So let's jump to that. So I'll have 1/2 capital M r dot squared, as I just talked through, plus 1/2 times a bunch of stuff. So we have m1 m2 squared plus m1 squared m2 over capital M squared times little r dot squared minus u of r. All right. Now, I'm running out of board space here, so I'm going to work up here, and we'll look at this quantity. So notice that in this quantity, I can pull out a factor, a shared factor of m1 times m2. And what I'm left with is m1 plus m2. In other words, capital M. So I have 1 power of capital M in the numerator, cancel 1 power in the denominator. So Lagrangian in new coordinates, let's just finish it off up here. We'll have L is equal to 1/2 capital M times r dot squared plus 1/2, I'm going to say mu times little r dot squared minus u of r, where mu is equal to, well, if I canceled my 1 power of capital M in the numerator with my 1 power in the denominator, I get m1 times m2 over capital M. Mu is called the reduced mass. And let's talk through what mu is in a couple of cases. Now, maybe the first most obvious case that we could think about is one in which m1 and m2 are the same. So in that case, m1 times m2 is m1 squared. Meanwhile, in the denominator, we have m1 plus m2, but that's just 2m1. So in that case, we would have m1 squared over 2m1, which is just m1 over 2. So in the first case, when these two are equal, mu is just half of the original mass of either object. Meanwhile, let's actually write out these cases. So case 1, m1 is equal to m2. We just talked through the fact that that means that mu is equal to m1 over 2. In case 2, let's deal with a case where m1 is much larger than m2. All right, well, that would imply that mu is equal to m1 m2 over m1 plus m2, but this denominator is approximately just m1. So this is approximately m1 m2 m2 over m1, which is equal to m2. Okay, so the reduced mass always sort of trends toward the mass of the lower object, of the lower mass object. And in fact, there's one more important point, which is that the reduced mass is always less than either of the included masses. So let's show that this is always less than mu1 without loss of generality, because mu1 and mu2 appear symmetrically in this equation. So mu is less than m1 if and only if m1 m2 over m1 plus m2 is less than m1. Now notice that m1 can be canceled from both sides of that inequality because m1 is non-negative. So that implies that m2, or sorry, I should say that's true if and only if m2 over m1 plus m2 is less than 1. But this is clearly true because one of the masses by itself must have less mass than the total mass of the two masses. All right, so we're good. All right, so now we have our Lagrangian. It's in terms of one term that involves just the center of mass and the total mass, and then another two terms that involve the reduced mass and then this deviation vector r. And this is actually really important. This Lagrangian, because it has two terms, and the generalized coordinates of these two terms don't interact with each other in any way. In other words, this term only has the big R coordinates, and these two terms only have the little r coordinates. Effectively, we have a problem that just splits in two. The Euler-Lagrange equations for capital R will only depend on this term, and the Euler-Lagrange equations for little r will only depend on the second two, or the second and third terms. Now, this is really nice, and we can deal with it, or we can sort of use this information in a number of ways. One of them is to say that, well, look, capital R is an ignorable coordinate for this Lagrangian. And I'll say Rj, right, for all of the components of R, is ignorable in L, which means that the total momentum of this system is conserved. So that's mr dot, the total momentum, is conserved. So the center of mass is just continuing on through time at a constant velocity. Another way that we could use this information is to say, well, look, this means that we can work in the center of mass frame, and that frame is not accelerating with respect to the frame that we're in already. So in that sense, we might as well just ignore the first part of this Lagrangian and start working with the effective Lagrangian involving only R. Okay, so let's move on to that. So now we'll have either, you could call this LR or L effective. Let me call it L effective, is equal to 1/2 mu r dot squared minus u of r vector. Now, let's take a step over here and look at our coordinate system. So the vector r1 minus r2, so for instance, this could be the vector r1 if this is the origin, and then this would be the vector r2. And r1 minus r2 is going to point from r2 to r1. Great. That means that the r coordinate system has its origin at mass m2. Okay. So what does that mean here? Well, I have that this force is central. And that means, or the force corresponding, I should say, to this potential energy is central. And that means that the force in this new R system is central in the other sense, that it's a force that points toward the origin or away from the origin. So U corresponds to a central force. i.e. one parallel to the r hat vector. Great. And a few lectures ago, we proved a really important result. We proved that any central force that is conservative must be spherically symmetric. So let's write down that assumption 2 is that the force between the objects is central, and that this assumption implies that U must be spherically symmetric. Now this is hugely important because it means that I can work in spherical coordinates for the r coordinate system. So now let's rewrite in spherical coordinates. I'll have L effective is equal to 1/2. Now, if I want the r hat dot vector squared, which is really what this is, I was being a little bit unclear in my notation, I know how to express that in spherical. That is mu r dot squared, where now this is just the r dot component squared, plus 1/2 mu r squared theta dot squared, plus 1/2 mu r squared sine squared of theta times phi dot squared minus u of r. Incredible. So now we can make a lot more progress in a specific coordinate system, and we can do that in the following way. Note that phi is an ignorable coordinate now. And that implies that the angular momentum in the z direction is conserved. But we see that something really useful is still available to us. We haven't picked x, y, and z axes. So what we'll do is we'll find the object's initial position, r, and its initial velocity, r dot. And we'll put both of those in the xy plane. So choose the xy plane such that r and r dot are in plane. Now, since LZ is conserved, and now in this case, the entire angular momentum vector points in the z direction, we know that at all points in the future, the angular momentum of this system will also point in the z direction. So this implies that L, the vector, is parallel to z hat for all time. And actually, let me just be clear here. We want to choose the xy plane such that r at 0 and r dot at 0 are in plane, because we have to have initial conditions for all of this to work out. Okay, now we have that for all time, L is parallel to the z hat vector. But because of the way that the cross product works, that further implies that because r vector cross r dot vector is in the z direction, that these two vectors remain in the xy plane. So we have motion that is always in the xy plane. That means that theta, as a function of time, for our choice of xy plane that we've already made, theta for all time is pi over 2. And if theta is pi over 2 for all time, then we can reduce this Lagrangian quite a lot because theta has become a constant. Okay, let me write that really quickly on this board, and then we'll start the next board with that written up. So we'll get that the Lagrangian effective becomes 1/2 mu r dot squared plus, well, this term that depends on theta dot squared has to be 0 since theta is a constant. Notice also sine theta is 1, so this next term just becomes 1/2 mu r squared phi dot squared minus u of r. Great. As I said, I'm going to clean up the board and we'll come back with that equation. All right, after a lot of work, we've been able to get our Lagrangian into this really simple form when we're only interested in the deviation between our two objects, which we called little r. Now, in the spherical coordinate system for that vector, we have the following Lagrangian. Recall that we still have that phi is ignorable. And therefore, the angular momentum, L, is conserved. So I'm actually going to use little l to match my reference, which is equal to dl d phi dot, and which, of course, in turn is equal to, well, I just need to take a derivative here. That's going to pull a 2 down here to cancel that 2, and I get mu r squared phi dot, and this thing is conserved. All right. Now, I want to make one final assumption, which is to say, perhaps we're interested in a Coulomb potential. Up to this point, we've been completely general. U could correspond to a spring force. It could correspond to the E&M force. It could correspond to gravity. So we would allow any of those so far. But now I want to think specifically about the Coulomb potential. I use the term Coulomb potential here, but in fact, I could mean the Coulomb potential between charges or the potential due to gravity. Both those have the same form, and so either one will work here. Recall that U, let's say for charges, is equal to K times Q1, Q2 over R, with a minus sign if the charges have opposite sign, which we'll assume here. We're interested in attractive Coulomb potentials. And U for gravity has a really similar structure. We have minus G M1 M2 over R. Now, before we go any further, we need to check what this is in terms of M and mu. But it turns out to be not so bad because mu is equal to M1 M2 over capital M by definition, which means M1 M2 is just equal to M times mu. So up here I can say minus G capital M mu over R. Good. All right. Let's use that and put it right into our Lagrangian. So I'll deal, because we're interested principally in orbital mechanics in this lecture, I'm going to deal with the gravity case. So the last term is going to be plus Gm mu over R. Great. Now, I basically already have the Euler-Lagrange equation for phi, so let me do it for R. I have that dl dr, well, that picks up a term from both of these. That is going to be mu r phi dot squared, then minus gm mu over r squared, and dl dr dot, well, that just picks up that term, so that's mu r dot. Together, these give me that mu r double dot is equal to mu r phi dot squared minus g m mu over r squared. All right. Now we're almost done. I want to take this equation and take phi dot squared and substitute in L, since I know L is conserved. So I want to use the fact that phi dot is itself equal to L over mu r squared to get an equation that is entirely in terms of r. Okay, so this would give me mu r double dot is equal to, well, if I multiply phi dot squared, that's L squared over mu squared r to the fourth, by mu r, I'll get L squared over mu r cubed, good, then minus gm mu over r squared. And I want to think about this equation because it really looks like the Newton's second law equation for an object traveling in one dimension with mass mu and subject to two forces. And in terms of thinking about orbital mechanics, one of the questions we often have is, well, is there going to be some sort of like bounded orbit? So is the trajectory going to be bounded in space? And if that's going to be the case, we kind of need the forces to be relatively close to each other. So let's think about this for a second. Let's sort of draw out what we see. So let's let this be the effective force, by which I mean everything on the right-hand side of this equation. Now, on the right-hand side, I have two power functions, one of them positive and the other negative. If I let r go toward 0, then it doesn't even matter what the coefficients are. R to the minus 3 is going to go to infinity faster than minus r to the minus 2 goes to negative infinity. So over here, I'll have my effective force diverging to positive infinity. Meanwhile, if I take things to positive infinity, if I take r to positive infinity, notice that r cubed is going to die faster than r squared. So I'll stay negative, but I'll trend to 0. So my shape is going to look something like this. Now, we're not really working in terms of potentials, but notice I could also integrate this. To get something like an effective potential. So what this would tell me, because if I integrate, I'll get, this looks like an effective force. So by integrating and then taking the negative, I'll get an effective potential. So U effective would be equal to what? So I have an r to the minus 3 here. That means I'm going to need a 1/2 and a minus sign here, mu r squared. Good, and that should be L squared, sorry. And then over here, I would need a plus gm mu over r, but I need to flip the signs because the force is the negative gradient of potential. Okay, so down here I would get a sort of similar looking graph. So let's say this is the effective potential, and here's r, and this has a sort of similar shape. And the point, especially in this second plot, let me get a marker, is that we have a local minimum for at least some values. So we might have, possible to have, a local minimum. So we might expect that we do get some bounded orbits where r, the r trajectory, is going to be sort of oscillating back and forth in the bottom of this well. All right. So we expect bounded orbits are possible for some values of the parameter. Of the parameters, I should say. Good. Now, I'm going to hop to the computer and we'll do something to figure out what the trajectory actually looks like over there. All right, let's begin with the effective Lagrangian that I've shown here, and remembering that the gravitational potential energy has this form expressed in the coordinate system that we're using. All right, so let's go ahead and apply that. Phi dot squared plus G capital M mu over R. All right, and now let's find our EL equations. The one for phi is easier, and we've already discussed it a bit. So we'll have dl d phi is equal to 0, and dl d phi dot is equal to mu r squared phi dot. And that implies that mu r squared phi dot is equal to a constant, and we call that constant L, which is the angular momentum in the z direction. Now let's do the R equation. So we will first do dl dr. From this term, we get a mu r phi dot squared. And then from this term, we do get a sign flip. So minus gm mu over r squared. Good. For dl dr dot, well, that just involves this term, and we get mu r dot. So for the R equation, we get mu r double dot is equal to mu r phi dot squared minus gm mu over r squared. Okay, and we'll say that this is a second equation that involves the new variable r double dot. Or I should just say, I guess, we need a second variable because we have two unknowns. All right, so let's group our equations here. We get the first equation, which I can rearrange. So I'll say it's phi dot is equal to L over mu r squared. And then our second equation, which is r double dot, is equal to r phi dot squared minus gm over r squared. These are our equations of motion. And our goal now is to try to solve them. But I have bad news. Right off the bat, if you go and look this up in a differential equations handbook, or you try to plug it into a software like Mathematica, what you'll find is that these diffie-qs don't have nice analytic solutions. But that is not the end of this story. Sometimes when we have two coupled ODEs, so in this case, we have an ODE for r and an ODE for phi, and they're coupled to each other, we cannot solve both ODEs to find r and phi as functions of time. But we can find r as a function of phi. And so we can proceed in that way. So new goal, find r of phi. The way that we're going to proceed here is using a substitution. We're going to say that u is equal to 1 over r. And that's going to lead to a new goal. We want to find u in terms of phi. What we're going to do is start with our r equation and try to get everything in terms of just u and phi. What that means is that we're going to find what the d dt derivative is in terms of a phi derivative and other things that depend only on u. Okay, let's begin. So d d phi by the chain rule is phi dot d d phi. I should say d dt is equal to phi dot d d phi. Now we can use one of our set of equations, one of the equations in our set to figure out what phi is. In terms of u, this is L u squared over mu. Okay. Now, where do we go from here? Sorry, times d d phi. Now, where do we go from here? Well, let's just take our equation and start doing replacements. So we get that d squared dt squared of r, which is 1 over u, let me just put that in right away, is equal to 1 over u times phi dot squared. We just said that phi dot is L u squared over mu. Okay, so that's squared. Minus gm over r squared. That's gm u squared. Okay? So now everything is in terms of u and t, and I need to get my phi's in there. And I'll do that by expanding this term on the left-hand side of the equation. All right, so this tells me that L u squared over mu d d phi of L u squared over mu d d phi of 1 over u is equal to, well, when I multiply this out, this is going to give me L squared u to the 4th over u mu squared. So that's L squared u cubed over mu squared minus gm u squared. Good. Now we're going to deal with this step by step, just so that we don't get too lost in the calculation. This is L u squared over mu times minus u to the minus 2 times u prime. So that's just from the chain rule here. But notice that that is then equal to, well, this u to the minus 2 cancels with this u squared. So that is just equal to L u prime over mu with a negative sign here. Okay, so let's carry this down. We're going to get L u squared over mu. Now I need to have my d d phi derivative act on the rest of this. So I'll pull that negative sign out. I'll pull out the L and the mu since those are constants. And I'll just get u double prime. And this is equal to L squared u cubed over mu squared minus gm u squared. Great. Let's get everything on one side and try to isolate u double prime by itself. So what I'm going to get is u double prime is equal to, well, notice this u squared can cancel this u cubed down to a u, and it cancels this u squared entirely. So everything gets pretty simple from here on out. Okay, so first of all, I will have a just u here, u double prime plus u minus gm mu squared over L squared, and that is equal to 0. Okay, and this is pretty exciting because this is a second order linear ODE with constant coefficients. And we know how to solve these. Now this is inhomogeneous, so it's going to be a couple of steps, but we do know how to solve them. Okay. So let's start out. We need to, well, actually, before we start out, let's non-dimensionalize this really quickly. Okay. U has dimensions of 1 over length. So I want to find a reference length to make this all nice. Notice that L has dimensions of, well, L is an angular momentum, so it's position or length times momentum. Length times momentum. Now, G times capital M is a little bit harder to deal with, but we can figure it out. The way to do so is to remember that Gm times another m over, or I guess times mu in this case, over r squared is a force, which implies that Gm is a force times length squared over mass. Now, force itself is mass times length over time squared, so then times length squared over mass. So in the end, we get length cubed over time squared. Let me also re-express L is length times mass over time. Sorry, length squared times mass over time. Great. And we're almost done because we also have mu, which is a mass. All right. And what all of this means is that if we take G m mu squared over L squared, that can be, 1 over that can be reference length. Sorry, so L squared over G m mu squared is, let me use capital L for this, L ref. It's my reference length. Right, because this would be the units, or the dimensions would be length to the fourth mass squared over time squared all over length cubed over time squared times mass squared. And here the masses cancel, the times cancel, and the lengths cancel down to just a single power of length. Okay, so our non-dimensionalizing is complete. Let's let U be equal to chi times L ref. What this ends up meaning is that we're just trying to solve the equation. We have a dimensionally well-defined system. So we end up just getting chi double prime plus chi minus 1 is equal to 0. All right. Great. So Now let's solve. First, we need to solve for a particular or a homogeneous solution. So we get chi h double prime plus chi h is equal to 0. Now that one is not too bad. The characteristic polynomial is just q squared plus 1. And so the characteristic equation is q squared plus 1 is equal to 0, which implies that q is equal to plus or minus I. All right, so this tells us that chi h is equal to a e to the I phi plus b e to the minus I phi. Good. Next, let's do a particular solution. So in this case, the guess is always that the highest order derivative vanishes. So here, we can just choose chi p is itself equal to 1. That makes everything work out. All right, so this all implies that chi is equal to a e to the I phi plus b e to the minus I phi plus 1. All right. Now, we can take this back to solve for u. It's already interesting that we found this reference constant, but going back to u now it is actually all right. So u is just equal to, let's say, a tilde e to the I phi plus b tilde e to the minus I phi plus, now to get from chi to u, we divide by L ref. So we get plus gm mu squared over L squared. And then to get to R, we take 1 over this. Now, in general, we'll have to put in our initial conditions in order to figure out what this a tilde and b tilde should be. But we can exploit something that's pretty interesting about this problem, which is that we haven't chosen the directions of our x and y axes yet at all. So I'm going to state without proof, and hopefully you can reason this out, that we can choose an x-axis such that we get a tilde is equal to b tilde. In that case, this becomes proportional to the cosine of phi. So we get something new. We'll get something like a tilde e to the I phi plus b tilde e to the minus I phi is equal to c tilde times cosine of phi by choice of x-axis. Okay, so now let's come down here. And sorry, before we go on, let me also note that we can figure out what c tilde ought to be. C tilde will be sum gm mu squared over L squared times what we'll call epsilon. We'll come back to this epsilon. All right, so let's pull out our L squared over gm mu now. And then what's left is 1 over 1 plus epsilon cosine of phi. All right. And this is our final equation. But we still need to unpack it. All right, so now this is our final expression, but we do still need to unpack it. So I'm going to do that in Mathematica. What I want to use here is the polar plot function, and I'll put this inside of a manipulator. Okay, so of course I'm going to divide out our reference length, and we'll just be left with 1 over 1 plus epsilon cosine of phi. And we'll go from phi is, let's say, minus pi to pi. Now we'll manipulate that for various values of epsilon. And epsilon could be any positive number. We do find that it has to be positive, otherwise we'll eventually exceed our domain. Remember that r needs to be a non-negative, really a positive quantity. Okay, so we'll go epsilon going from 0.01 to 5. Okay, so we see that as epsilon goes to 0, what we get is a circle. Meanwhile, if I make epsilon larger, I start to get an ellipse that gets more and more and more elongated, until at epsilon 1 I see some interesting behavior. At epsilon equals 1, suddenly I have something that never returns. I get what we would call an unbounded orbit. Then, for epsilon larger than 1, I get something very strange indeed. These two, this x in the middle here, that's an artifact of the way that Mathematica is plotting this. And really, the trajectories that are allowed are these two over here, which are called hyperbolas. Okay, so the different types of behavior. I get a circle for epsilon going to 0. I get an ellipse if 0 is less than epsilon, which is less than 1. At epsilon equals 1, it's not obvious from what we saw there, but I get a parabola. And lastly, I get a hyperbola when epsilon is greater than 1. Okay, now some of these are basically obvious, right? The circle being what happens when epsilon goes to 0 is clear because if epsilon is 0, then I just get r is equal to 1 in my non-dimensionalized units. And for the ellipse, if you know the polar equation for an ellipse, this is it. So there's maybe nothing surprising there. But really what's interesting, or what's useful to show, is that we get bounded behavior when epsilon is less than 1, and unbounded behavior when epsilon is greater than 1. To figure that out, let's look at what the maximum of this function is as a function of epsilon. All right, so in case 1, we have epsilon is less than 1. Now in that case, r is equal to 1 over 1 plus epsilon cosine of phi. And I can just take my various values of cosine to figure out what the bounds are. Because if cosine is, so if, if cosine goes to minus 1, I'll get 1 minus epsilon. Oops, on the side, 1 over 1 minus epsilon. And on the other hand, if cosine goes to plus 1, I'll get 1 over 1 plus epsilon. Great. And the key is that both of these values are greater than 0. Meanwhile, if epsilon is larger than 1, then there exists some phi such that the denominator diverges to infinity, and so r becomes unbounded. So let's say that's case 2. Meanwhile, if epsilon is greater than 1, then there exists, running into my head here, there exists phi such that 1 plus epsilon cos phi is equal to 0, and the denominator diverges. All right. Lastly, let's just think about what this means for, a star-planet system or electron-proton system. What we've found, here we go. What we found is that there are some solutions which will, because of the particular initial conditions, keep the smaller object bound around the larger object. But if the smaller object comes in with, for instance, too much velocity, it just won't be caught in a stable orbit. Instead, its trajectory will be changed, but then it will be ejected. All right. Now, that's all I have to say about this. I'm going to hop back to the board and we'll talk a little bit about Kepler's third law. Now, I want to finish off this video by talking about Kepler's 3 laws. Kepler's laws are not like Newton's laws. Newton's laws provide a foundation for us to solve problems related to Halley's second question. Given known forces, can we find the trajectory of an object? Kepler's laws are more like empirical observations that display simple relationships between things. They came about in the first half of the 17th century because Kepler was working largely with data. He was able to see these simple power law relationships because he could see it in the data. So let's go through Kepler's laws and we can kind of see how maybe that's the kind of thing that you might be interested in if you have a wealth of data but not good models to predict why the data behaves the way that it does. All right, Kepler's first law is that planets travel in ellipses. With the star, their star, let me say, at one focus. Now let's look at the solution that we've already drawn up. We've found that r, as a function of phi, is equal to some constant, I believe it's L squared over G m mu squared times 1 over 1 plus epsilon cosine of phi. Great. Now let me draw a picture to illustrate what we've seen so far. So here we have our object. I'm going to say r naught is this length here. And so we have that at phi equals 0, we are at r naught. Sorry, we're not at r naught. We're r naught over 1 plus epsilon. Good. Now, when phi is equal to pi, we are instead at r naught over 1 minus epsilon, which must be bigger because epsilon is between 0 and 1. And so a smaller denominator is going to make the whole object bigger. Okay, so over here, this length is r naught over 1 minus epsilon. Great. And what we find is we have an ellipse that sort of connects these two. So as it turns out, the origin is one focus. So we just write this down here. Origin is a focus of the ellipse. It's very common in terms of, or when we work with ellipses, to work not with these two distances, but instead with the so-called semi-major and semi-minor axes. So let's draw those. The semi-major axis is what we get if we take the ellipse, we sort of cut it in half the short way, and then we measure this distance. So I'll say that that's A, which is the semi-major axis. The semi-minor axis is what we get if we slice it and then look at the short length. So that's this distance here. We'll call that B. So A is the semi-major axis. And B is the semi-minor axis. All right, good. Now, I want to express the semi-major and semi-minor axes in terms of R naught and epsilon. But note that we've actually already shown Kepler's first law with what we've done, because the ellipse that we found back on the computer is exactly one such that the origin is one of the foci. So if the origin is a focus and we find that this is traveling an ellipse, then we've found Kepler's first law specifically. But the semi-major and semi-minor axes are going to continue to be important, so let me re-express things in terms of them. Now, notice that the semi-major axis is what we get, if we double the semi-major axis, I get what we could call the major axis, the entire length of the ellipse along its long side. But that's also the sum of these two. So notice that I have that 2a is equal to r naught over 1 plus epsilon plus r naught over 1 minus epsilon. Now let me get a common denominator and combine these. I'll pull out an r naught, and then the common denominator is going to be 1 minus epsilon squared. Good. Now from the first term, I'll get a 1 minus epsilon. From the second term, I'll get a 1 plus epsilon. But notice that the epsilons cancel. So this gives me 2r naught over 1 minus epsilon squared. In other words, A is equal to what? R naught over 1 minus epsilon squared. Great. Now, finding the semi-minor axis is a bit more challenging. I'm going to take a sort of interesting tack here. I'm going to say that the semi-minor axis is the y value that is the maximum y value of the ellipse. I can get the y value by just taking r times sine of phi. So I want to take r sine of phi, and note that that is going to be r naught sine phi over 1 plus epsilon cosine of phi. And then I want to find the maximum. So I'm going to take a phi derivative of this. Okay. So the quotient rule tells me that I need to take r naught cos phi and then times 1 plus epsilon cos phi minus r naught sine phi times the derivative of what's in here, which is minus epsilon sine phi, and then take that over 1 plus epsilon cos phi squared. But I'm only interested in where this is equal to 0, so I can ignore the denominator entirely. Notice that an r naught comes out. I get a 1 cos phi, then an epsilon cos squared phi. Then, because of this minus sign, I get an epsilon sine squared of phi, and that's equal to 0. Now I use my Pythagorean identity. I find r naught cos phi plus epsilon is equal to 0. And therefore, I find that cos phi is equal to minus epsilon. Great. Okay, but that's not actually the value that I want. What I want is this value up here, which is r naught sine phi over 1 plus epsilon cos phi. Okay, so if I take that, what I'm going to do is I'm going to say this is r naught 1 minus root 1 minus cos squared of phi over 1 plus epsilon cosine of phi, and then just stick in minus epsilon everywhere that I need to. So I get r naught root 1 minus epsilon squared over 1 minus epsilon squared. Or in other words, r naught over square root 1 minus epsilon squared. Great. Okay, so this is B. Let's just highlight that we've now found both of those. And move on. Now, as we do the rest of our calculation, we'll try to do the majority of our computations involving A and B rather than R naught and epsilon. Okay, so for Kepler's second law, I'm actually going to skip a big explanation other than to say that we already covered this in our video on angular momentum. Recall that what this law says is that if we have two arcs which are swept out in the same amount of time, let's say delta t, then the areas in these two regions, so let's call them A1 and A2, are the same. A1 is equal to A2. Another way to say this is that the area swept out, so if I say that A is a function denoting the area swept out, then as a function of t, this is equal to a constant. Good. Okay. Lastly, we have Kepler's third law, and this is where we're going to need everything that we've shown so far. Kepler's third law gives a power law relation between the period t of rotation and the semi-major axis. Great. Now, deriving Kepler's third law is quite a bit more challenging than deriving the other two, but it is fruitful. We're going to begin by noting what this constant is here in Kepler's second law, which you can go back and find from our video where we derived it. This constant turns out to be the angular momentum over 2 times mu. In that video, we would have said m, but here our effective mass is mu of our one object. Great. Now, I want to figure out what L is, because I wouldn't like to work with L directly. Instead, I'd like to work with R naught. Okay, so that's not too bad. R naught is equal to L squared over G capital M mu squared, which means that L squared is just R naught times that stuff. So this is equal to the square root of G times capital M times little m, times mu squared R naught over 2 mu. Notice the mu's cancel. Oh my god. That's bad. Notice the mu's cancel. Then I want to take R naught and replace it by the semi-major axis. So this is then the square root of G, let me say actually, I'll pull the 1/2 out. 1/2 the square root of Gm times the square root of A 1 minus epsilon squared. Good. All right. Now I have this, and I know that I can get the total area by integrating from 0 to the period dA dt with respect to t, but I know that that is just this constant times the period. So that's 1/2 root gm root a times 1 minus epsilon squared. Good. But on the other hand, I know that times t. On the other hand, I know what the total area of an ellipse is. It's famously pi times a times b. Good. Okay, so I have a square root of a on this side, an a on that side, and by combining, one more point here. I actually don't want to have the semi-minor axis involved here. So I want to replace b by a, but I know how to do that here. You'll notice that b and a are related by a factor of root 1 minus epsilon squared. So this area could also be expressed as pi a squared times root 1 minus epsilon squared. Great. So now we have this equation. Pi a squared root 1 minus epsilon squared is equal to 1/2 root gm root a times 1 minus epsilon squared times t. Note that the factor that involves the eccentricity cancels. The a's, on the other hand, cancel down to a 3/2 power. So that a cancels this 2 to a 3/2. And by moving things around, I get that t is equal to 2 pi a to the 3/2 over square root gm. All right. Now this is fine, but you often see this given in a slightly different format. What we would do is square both sides to find that t squared is equal to 2 pi quantity squared a cubed over gm. Now Kepler's third law is usually stated t squared is proportional to a cubed. And that is the format that Kepler understood it in. Now this was very nice when you're looking at data because you can easily measure the period of oscillation, or the period of orbit of a given planetary body. And it turns out you can measure its semi-major axis without too much difficulty. So this was a great way to see if the data sort of fit this model generally for all planetary systems, and of course they did. This contribution later led to Newton being able to explain all of these laws in much the same way that we're doing, and then in the Lagrangian formulation for us to be able to explain it in this even more nuanced way. In any event, I hope that you've enjoyed this thorough look at orbital mechanics, and next week we'll be doing a totally different topic. We're going to talk about systems that are not in inertial reference frames. I hope to see you in that one. Bye-bye.